Alright, so I am going to talk about the atom, the many different models of the atom that have been created, and some of the few experiments that have given us our basis as to whether or not a model is correct, and have the experiments have disproved certain models in the past. So this is the plum pudding model, and this model was suggested by J.J. Thomson, who discovered the electron, or what we now call the electron. It was back then it was just a negatively charged particle that they observed. And what J.J. Thomson suggested was that an atom was basically just a clump of positively charged matter, and within that clump was just a bunch of electrons floating within the clump of positively charged matter. And so this is today called the plum pudding model of the atom, and for a fair amount of time it was believed to be correct, since J.J. Thomson discovered the electron, and um, that was such a huge feat that it would be hard to disbelieve what this man said. So that was believed for a fair amount of time. Later on, the planetary model was made, and so this model is essentially a grouping of positively charged particles that are called protons and neutrally charged particles called neutrons within the nucleus. And there are what are called electrons, which are negatively charged particles, much, much smaller, much, much lighter, that are orbiting the nucleus due to the speed at which they are traveling, excuse me, as well as the charge that they have. So since electrons are negatively charged and protons are positively charged, there is this constant, I guess you could say, battle between the speed at which the electron is traveling and the pull that the positive proton is enacting on the electron. Um, so as you can see, in this case, the electrons are not within the nucleus themselves. In fact, they're in they are in what is called, commonly known as a shell of electrons. And so the electrons here are orbiting in a shell that can only contain 2 electrons. Based on what level of energy you're at, there can only be a certain amount of electrons. So for example, in this shell, there can only be 2. In the next one, there can be 6, even though there are only 4 electrons shown in this one. So this is Bohr's model. Bohr created a model of what happens when a photon hits an atom. And so when a photon hits an atom, there is energy that is transferred to the atom itself. And what this does is often it bumps up an electron to the next level. This can only happen with what are called valence electrons, which are essentially electrons that are part of a shell that is not complete. So if we go back to the previous one, these 4 are valence electrons. These 2 are not. They are in a shell that is complete and cannot be affected by this. So what Bohr suggested is that when this photon hits the atom, the electron will bump up an energy level and essentially give off a certain wavelength of light based on A, the atom, and B, the level at which the electron was moved up to. So there are 6 levels that we can view. There are technically, theoretically, more. However, as you get to the higher levels, they cannot exist because of radioactive decay and the atom gets essentially so heavy that the forces that keep the nucleus together are not strong enough, and so there are technically, theoretically, more levels than 6, but they don't exist in. We can't view them, but theoretically they exist. Okay, so the gold foil experiment, which is also known as the Rutherford experiment, was the experiment that officially proved J.J. Thomson's plum pudding model as incorrect. And so what the experiment was set up to do was essentially there was an alpha particle emitter here that passed through a slit surrounded by a screen that would be able to detect light, and in the middle there is gold foil. And had J.J. Thomson's model been correct, what would have happened, since alpha particles are rather heavy, the particles theoretically would have just passed through the foil straight with maybe a few minor reflections, but nothing too big. But what was seen instead was a vast array of different reflections in different ways, and so it was instantly proved that J.J. Thomson's model of the atom was not actually correct. That it wasn't actually what an atom was like, and this proved that the electrons were not actually within the atom either. Okay, so binding energy is defined as the mechanical energy required to disassemble a whole into separate parts. And so when applying this to nuclear physics, you can think of binding energy as also being equal to the energy released when a nucleus is created from other nucleons or nuclei. And so that is nuclear binding energy, and then there's also atomic binding energy, which comes from the electromagnetic interaction, and it's the energy required to basically take apart an atom into free electrons and a nucleus. And so atomic binding energy, if you wanted to remove an electron from an atom, that is the energy that you want to think of, and it's also known as the ionization energy, because when you remove an electron, well, the atom becomes an ion. Right. So similarly, work function is defined as the minimum energy needed to remove an electron from a solid to a point that is just outside of the solid. So this means that the electron position is far away from the surface on the atomic scale, but is still very, very close to the solid itself, and it can still be influenced by different factors when it is removed from the solid itself. Okay, so lastly, I want to explain what the current day atomic model is and what we understand of the model today, as opposed to what we did back when the planetary model existed and the plum pudding model had just been disproved, and around that time. So back then, they believed that there were 3 subatomic particles that made up the atom, and those were the proton, the neutron, and the electron. And today, we know that protons and neutrons are actually made up of what are called quarks. And quarks, in terms of what are found in neutrons and protons, are they consist of up quarks, which are denoted on here as U, and down quarks, which are denoted as D. And so when you have two down quarks and an up quark, you end up with a neutron, and when you have two up quarks and a down quark, you end up with a proton. And if you look at the size of this atom, it gives you an idea as to just how small this actually is. The nucleus itself is 10 to the negative 14th meters, and the size of an atom is about 10 to the negative 10th meters. And I really like this right here. It says, if the proton and neutrons in this picture were 10 centimeters across, then the quarks and electrons would be less than 0.1 millimeters in size, and the entire atom would be about 10 kilometers across. So that gives you an idea as to how small the nucleus is in comparison to the entire atom, and how small a single electron is in comparison to the nucleus and then the entire atom. And I think that's a very good comparison. So this is our current understanding of the atom, and there may or may not be more discoveries in the future. There's always people that say, oh, we found everything there is to find in physics, and then suddenly you find something else that disproves a bunch of stuff you found before, so we won't know for sure. But this is our current understanding of the atom.